let's take a look at an object here that's rotating. So from an overhead point of view, you can picture this as a door rotating about a hinge here, hinge and door. I'm going to have it rotating around like that. And the question is, what is the total kinetic energy? Well, to find that we know the formula, 1/2 mv squared, except what is the speed? Because if I have something that's rotating around in a circle, the speed at this point is greater than the speed at this point. Because remember that speed is distance over time. And if I have this thing rotating around in a circle, well, that travels a much greater distance than this point does. But it takes the same amount of time, assuming it's a rigid body. So we are doing rigid body physics here. You get into a little bit more advanced engineering courses when you start dealing with non-rigid bodies. So as this thing is spinning around, then there's a relationship here between v and omega. Well, I know the distance is going to be 2 pi r over time, where r is the distance from here to wherever the point is. So the speed, it doesn't actually have to go all the way around in a circle. It could just go from here to here. Some arc length s. There's an angle here, theta, that it goes through. And so I know that, oh, actually technically it's delta theta. So I know that speed is distance over time, so that's just going to be the arc length divided by time. Well, the arc length, based upon the basic relationship, is r times this angle right here. So this is r delta theta over delta t, which is r delta theta equals r delta theta over delta t, which is r omega. So the speed is equal to r times the angular speed. This is a relationship that we will use again and again. So back to this. How do you deal with something that is not traveling all at the same speed? Well, I could just pick the middle here, and that might come up with a crude estimate for it, because I can find the speed at this point if I know that distance r there. In which case, k estimate 1 would be 1/2 times m times whatever that speed in the middle there, which is just, if this length here is L, this would be L over 2 times omega squared. And that's a rough relationship. However, I could get better if I broke this stuff up into two pieces. So k estimate 2 is 1/2 times, well, let's do the lower half first. So 1/2 times, well, that's half the mass of the door, so half the mass, times L over, well, that's a fourth of it, so that's 1/4 L times omega squared, plus, this is for the lower half, and then the upper half is 1/2 times half the mass times 3/4 L omega squared. And we get a slightly better estimate, but why stop there? Why not break it up into 4 pieces or 5 pieces or 6 pieces? And so what we are going to do ultimately is break it up into an infinite number of pieces. So if I have the door here, and I break it up into an infinite number of pieces, then the kinetic energy is just, well, 1/2 times the mass of the first piece times its speed squared, plus 1/2 mass of the second piece times its speed squared, plus and so on, up to 1/2 times mass of the nth piece times its speed squared. So I break it up into n number of pieces. I'm eventually going to let n become infinitely large. I can shorten this to the sum of 1/2 m sub I v sub I squared, where I goes from 1 to n, or infinity ultimately. Remember that the mass here is basically the mass of the entire door divided by however many pieces, assuming I break it up into in even pieces. Well, this is just a sum here, so let me factor out what I can. So I know 1/2 is common to everything, so I could factor 1/2 out. So that's 1/2 times the sum of mi vi squared. And I know from what we did on the previous page and earlier in this semester that v is equal to omega r. So this would just be equal to 1/2 times the sum of mi times omega ri squared. Now this omega is the same for everything. Again, we're dealing with rigid body rotation, and so everything is rotating at the same angular speed. And so that's a constant. So I could actually factor that out. So I'm left with a 1/2 omega squared. Again, there's no subscript there to indicate this, times the sum of mi ri squareds. And this right here, that is the moment of inertia. It's just the sum of all the tiny little mi's and ri squared. So this ultimately ends up being 1/2 I, that's I, omega squared. Now, for 151, you're left with, great, how does that help you? Well, this helps you a great deal, and I'm going to pause this while I find the reference. That trying to figure this out is there are some certain shapes where it's already been calculated for you. And so for 151, I refer you to page 357. And for 251, I refer you to page 365. Every beginning textbook has a page with these basic shapes in it. Now for 251, I'm going to go through the derivation of one of those shapes. 151, you sort of trust that it's there. And that is moment of inertia. And we will stop it.